Planning energy systems is quite often a top-down process, so that the planner starts from what they want to produce, and that is in most cases only electricity. And then they install a system, or they figure out the costs to install a system to produce and distribute electricity. This is not necessarily the best way when you want to start off a new business and start a new system of energy inside an already existing electricity distribution network. Because if you want to compete with the electricity prices provided from large-scale fossil fuel-fired plants, then you might end up in great problems. So we shall here start from another perspective. We shall start from a bottom-up perspective. And that means that the first thing you shall do is to identify the market for energy services in the region. And we shall now spend a lecture around 45 minutes on energy services, and to identify different types of energy services that can be used as a basis for the market. The first thing you need to do when you want to identify the market for energy is to identify the real needs of the customer. And these needs are typically not to get energy, but to get energy services. Now, at the course site, you will find a side reading, which is the World Energy Assessment, which we shall now go into. The World Energy Assessment was a report issued by the United Nations in the year 2000. It's a solid set of data, about 500 pages in total, but you need not read all of it. However, you need to identify and learn some definitions so that we all speak a common language as we go on further along the course. So you log into the course site, you go into the course material folder, and here you will find a subfolder called Side Reading Material. And in that subfolder you will find a document leading you further on to the World Energy Assessment. So we're opening up Reports and Side Reading, and we're getting into the document that leads us further on to the World Energy Assessment. In the World Energy Assessment we shall look at Chapter 6, which deals with end-user efficiency and with energy services, and especially we shall now have a look at Figure 6.1 in Chapter 6. Now this is Figure 6.1, which deals with energy conversion steps, types of energy and energy services, and potentials for energy efficiency. The figure starts with the raw materials, extraction and treatment of the primary energy carrier, be that gas or coal, uranium or oil, or biofuels, as noted here with the word agroforestry. The primary energy is then the biomass in our case, as shown in the right-hand side end. And that is what you shall ultimately come down to, what biomass is best used for the customer and for the customer's need. But in this course you will start from the other end. You will start from the customer perspective. Right now we will go down through this figure successively and have a look at the different steps that come between the extraction and treatment until the customer finally gets the energy. So you notice that we start with extraction and treatment. We then get a primary energy carrier, which is the biomass itself. It can be converted into something through a conversion process, which might be an upgrading, but might not be necessary. The fuel then, the upgraded fuel, must be distributed, and it can be distributed by different ways depending on the quality. And it will finally give us something we call the final energy. You will notice the green frame that ends here. That is where the responsibility of the energy sector companies typically end. So the energy sector will deliver a final energy to, or a final energy carrier to the customer or to a distribution network. The final energy carrier, be that charcoal or ethanol or electricity or district heat or anything else, is then converted into the final useful energy by the customer. And that can be done in an oven, in a boiler. It can be done in an electric arc furnace, a light bulb, TV set, a freezer, a stove, or anything. That gives the customer a useful energy, which is then heat from radiators, or cooling, or heat for melting of metals, or maybe for burning ceramics, or maybe cooling, or something else. This is still not what the customer ultimately wants, but at the bottom line of this picture, you will now see what the customer actually wants, and that is an energy service. The customer might want space conditioning, space comfort heating, indoor climate. The customer might want to make steel, or to have molten steel, molten glass, or burnt ceramics. The customer might want to have food preservation, or maybe cooked food. The customer wants a service. The customer does not want energy as such. So the customer will have a need of an energy service. The customer might or might not have some kind of a conversion apparatus for the conversion of final energy carrier into useful energy. That apparatus, that machine, whatever it is, that equipment, might be fitted for a certain type of energy carrier. That energy carrier might be best produced using a certain conversion technology. That conversion technology might be best suited for a certain primary energy carrier, which will then go back into what kind of raw material shall be extracted and how it shall be pre-treated to fit the final need. So what you shall do in this course is that you shall work your way through, starting at the customer need of an energy service, and you shall go all the way back through this chain to the raw material that is best suited for that type of energy service. This is the other way than many people often think of energy supply systems. Very often, energy supply system planning starts with the raw material and then tries to fit the raw material into an already existing chain. But you have another situation, because you are now starting a new supply chain from a new raw material that has previously not been used to any great extent in your energy system. So what you shall do is that you shall try to identify a market segment where the customer need is best supplied from a raw material that you have, and you shall identify the whole process chain. But you shall start with a customer perspective. What is the customer need of energy services? So the first thing you shall do in this course is to identify the customer energy services and the need of energy services. So that is your first task. So let's now have a look in the course book to see what that has to say about energy services and the customer needs. When you scan through the contents of the course book, you will notice that it's quite extensive, but that no place does it actually mention energy services. Actually, it hardly mentions the customers at all. So, as a starting point, we will go back to section 2.7 in the beginning, and we will have a fast look at what it says in that section. The course book then defines that there are mainly three different types of primary energy to be produced, and that is heat, its mechanical energy, and its electricity. And then it discusses these on pages 17 and 18, but not in any great detail. We shall now have a look at the heat and see how heat can be split into different types and different qualities, and we shall introduce two fundamental thermodynamic terms, namely exergy and energy, which are not mentioned in the course book at all, but which you need to know before you go out to try to identify the customer's needs of energy services. To introduce the concept of exergy, and hence also of energy, we need to go back to 1824, when the French artilleryman and engineer Sadi Carnot was publishing a paper called Notes about the Mobility Force of Fire. Now, his work is considered one of the most original one in the history of physics. What he did in this work was to discuss an ideal process to transform heat into mechanical work. And the basis for this process is shown in the diagram. The basic concept of the so-called Carnot cycle is shown in this diagram. We start off with the cylinder. At the right hand side it has a piston that can be moved, and from the beginning the cylinder is filled with a gas with the temperature T sub 1. The piston is in that case in position 1. Now, to this starting situation we now add an amount of heat to the gas in the cylinder, and that is Q sub 1. As the gas is heated, it will expand, and it is assumed that the gas expands at a constant temperature T sub 1 until the piston has moved to position 2. After that, the gas is again allowed to expand further until the piston is in position 3, but during this expansion the gas may lose temperature. So the first expansion from 1 to 2 is at a constant temperature T sub 1, while the second expansion from 2 to 3 is while the gas loses temperature. This is indicated by the slightly bluer color in the diagram. As the gas has now expanded and the piston has moved from position 1 to position 3, there has been external work done by the moving of the piston. So that work can be used theoretically to, for example, turn around a generator or something else for any kind of mechanical work. So the piston is now in position 3 and the gas has some kind of a temperature. Now the third stage in the cycle is that we bring the cylinder into contact with the cooling source so that we start extracting temperature from the cylinder, and the amount of energy that we extract is Q sub 2. As the gas then cools down, it will shrink, and what happens is that the piston will move from position 3 to position 4. The gas will now have temperature T sub 2 in the cylinder, and then finally we move the piston, so we compress by adding external work to the piston. We compress the gas, moving the piston from position 4 to position 1. The cylinder is now thermally insulated, and as we compress the gas, the temperature will again increase, and we assume that the temperature increases back to the starting temperature, T sub 1. So the compression, the amount of compression, that is the relation between positions 4 and 1, the amount of compression, is such as to bring the gas back from temperature T sub 2 to temperature T sub 1, which was the starting point. Then this cycle can then be repeated over and over again, and this cycle is called the Carnot cycle. The Carnot cycle, as illustrated in this diagram with the two axes T for temperature and S for entropy, shows us how much mechanical work can be extracted from an ideal gas engine when the working medium in the engine, the gas, cycles between the two temperatures T sub 1 and T sub 2. Into the engine is also put heat energy, the amount equal to Q sub 1. And the total amount of mechanical work that can be extracted from such an engine is the quantity W. Now, this makes it possible to express the Carnot efficiency, and you will notice that the Carnot efficiency is a function only of the two temperatures, at the heating source and the cooling side of the engine. This Carnot efficiency is the simplest way to introduce the fundamental concept of exergy, and it is a very fundamental quantity valid for any kind of heat engine that works between two temperatures. So, we have now defined the Carnot efficiency, which is a simple measure of what fraction of exergy is present in a certain fuel. Now, the exergy content is not a fundamental thermodynamical property that goes with the fuel, but the exergy is actually a thermodynamical function of state, because it is dependent also on the surrounding. However, we will now regard exergy in the forthcoming discussion in a surrounding where the temperature is always 20 degrees C. Now, before we go into looking at temperature and heat as a service, we shall remind ourselves that our customers are never actually willing to pay neither for oil or coal or gasoline or electricity per se, but the reason that the customer is willing to pay is because these energy carriers can provide a certain energy service, and it's the service that the customer is paying for. Now the textbook in section 2.7 did put the finger on 3 different types of energy products. That is heat, but the textbook was concentrating only on comfort heat and domestic heating, and we will widen that scope now a little bit. The textbook points out mechanical work, and in modern society that is mainly the operation of cars and transportation fuels. And then the textbook points out electricity, which is what commonly is regarded as the major product. Now we will turn this reasoning a little bit upside down. Producing electricity from fuel will always produce surplus heat. That follows from the simple fact that only the part of the energy that is exergy can be converted into electricity, and the energy content of the fuel will always be lost, no matter what process you use. So if you start with a fuel that has a high energy content, then the total efficiency in your electricity production will by necessity be very low. Hence, you should only produce electricity if you can find a use for the surplus heat. Basically, the same thing holds true for the production of car fuels. The idea with upgrading something into a car fuel is that in the car fuel you want to have the highest possible concentration of exergy. And that means that if you start from a fuel that has a low fraction of exergy and you want to convert that into a fuel that has a high concentration of exergy, then you will lose all the energy. So there will be a heat loss. And just like with electricity production, you should only go for the production of a car fuel if you can find a market for the heat lost. Basically, this reasoning holds true also for biochemical conversion processes, but in these cases there is a heat loss which is at about 37 to 40 degrees C, and the remaining energy loss is in the form of carbon loss, which is still left in the residues from the digestion process or from the fermentation process. Now, here we will concentrate on thermal conversion, and in these cases the heat loss is available at a higher temperature. Biochemical conversion is different, but the main reasoning in this lecture is based on thermal processes and not on biochemical conversion processes. So any type of high efficiency energy process will demand basically that there is a heat sink available to take care of the energy losses. Now the quality of this heat loss, of the surplus heat, may to some extent be set by process design, and to some extent so may the total power, the total amount of surplus heat. But you can never avoid to have heat losses when you're treating a fuel, whether you want to produce electricity or you want to upgrade the fuel into, for example, a car fuel. So to get an economically viable process, the most crucial thing is to identify a market for the heat, and to do that you have to identify the heat sinks that are available in the region. To identify the different heat sinks, we shall start with the temperature axis extending from minus 273 degrees C up to 2000 degrees Celsius. This is the range in which we can find different types of energy services that are directed or can be characterized by temperature. Starting with comfort and climate heating, that's only around 20 degrees Celsius and nothing else. Whereas hygienization processes, for example within the food processing industry, might extend from say plus 100 degrees up to about plus 250 to 300 degrees. Food preservation and processing extends from freezing temperatures, say minus 50, up to about 300 degrees for heating and heat treatment. Whereas steam for electricity production ranges from about 300 degrees up to about 600 degrees, 550 to 600 in modern steam applications. Aluminium processing extends from about 500 degrees up to around 800 degrees, whereas the annealing of steel requires higher temperatures, from about 700 to 900 degrees C. The production of building brick occurs at temperatures around 850 up to about 1100 degrees C. Glass processing, depending on the glass quality, from about 1000 degrees up to 1600 degrees. Cement production from about 1300 up to 1600 degrees. Steel making from about 1400 up to about 1750 degrees C. So there's a range of different types of temperatures that need services. And changing now the scale from temperature into the fraction of exergy in the fuel or in the process needed to run the process, you will notice that if we fix the surrounding temperature at about 20 degrees C, and we then calculate the Carnot efficiency for the different temperatures, you will notice that we get a negative exergy, minus 6.8% exergy at 0 degrees. We get 62.1% exergy as a demand for processes that shall run at 500 degrees C, and we get 77% exergy demand for processes that shall run at 1000 degrees, up to 87% for processes running at 2000 degrees. Let's now look at what biofuels can supply us with. And in this diagram you will see the fraction of the energy that is exergy on the left-hand side axis, on the vertical axis, extending from 78% up to 90%. On the horizontal axis you see the moisture content in the fuel, extending from 0% completely dry fuel up to 60% water in the fuel. And the three different curves indicate different combustion conditions where we have excess oxygen as a measure, the excess oxygen in the dry gas from the combustion plant at 2%, 5% and 7%. You will notice that wood fuels, even at 60% moisture and even in a low efficiency combustion situation with 7% oxygen, have about 80% of the energy in the form of exergy. So even a very wet wood fuel can provide a lot of exergy. If we now change and look at herbaceous fuels, you will notice how the amount of exergy is lower with herbaceous fuels than it is with wood fuels. But still, in most cases, it's exceeding 78%. Looking now at what can be achieved by open air drying, we typically end up with a fuel with something in between 13 up to a little bit more than 20% moisture content after an open air drying. And that means that we would typically arrive at exergy contents exceeding about 84%. So basically any biofuel will work for any process that requires less than about 84% exergy. So at least up to 77% exergy, which is equal to 1000 degrees process temperature, we can use basically any biofuel. Whereas quite a few biofuels will work also for the highest temperatures, the highest amounts of exergy. So biofuel can be used to provide energy services up to temperatures around more than 1500 degrees, not only for comfort and climate heating. However, there are some limits that need to be taken into account when you want to figure out where biofuel is most competitive. At about 50% exergy, about 300 degrees C, there is the first limit. Because to arrive at only 300 degrees C on a sunny day, you need only concentrate the solar irradiation 30-fold. So for temperatures below about 300 degrees C, solar energy might well be very competitive to biofuel installations. This is, of course, unless other factors are determining. If you want to use solar energy, then you will have to accept that it might be intermittent. It will not be available during night. It will not be available on cloudy days. So if you are demanding a reliable supply, then solar heating is not an alternative, even for these low temperatures. But then you might well have biofuel as the main alternative. For cooling, the limit looks a little bit different. For cooling production from fuel firing to be very efficient, you need to get rid of a lot of surplus heat. And unless you can sell that heat, most probably your process will not be economically viable. Hence, you need a heat sink close to the cooling production facility. And if this cannot be arranged, then the cooling should be produced using compressor coolers, and the biofuel should then be used in a CHP plant. But that depends entirely on where the cooling need is situated geographically as compared to the heating need. So for cooling production, you will end up with very specific requirements on the geographical area. You need a cooling sink or a cooling customer, and you need a heat sink or heat customers to be present in the same area. Otherwise, cooling production from fuel firing is not a good alternative. So then, what you shall do for your own region is to identify the total cooling power needed at temperatures from, say, +5 degrees up to ambient. You should identify the total power needed to provide heating temperatures from, say, about ambient up to 300 degrees. You shall identify the total power needed to provide temperatures between, say, 300 degrees and 1200 degrees C. For these temperatures, we can use any biofuel basically, and solar heating is not a competitor in this temperature range. You shall also identify the total power in watts needed to provide temperatures exceeding 1200 degrees C. To arrive at these temperatures, we would need to upgrade the biofuel and not to use the raw fuel as such. You shall also identify the limiting factors for the willingness to pay for these different types of energy. of energy services, I should say. Is the limiting factor the reliability of the supply? Is the willingness to pay limited by the cost of the energy or the energy service? Is there anything else, like local environmental considerations, or what do I know? You have to identify that for your own region. And finally, you also have to identify where geographically these needs occur, so that we can ultimately identify any co-production options and synergy effects. And then once these customers, once the market is defined and the market is split into these different energy services, you can ask yourselves, and we shall ask ourselves together, how much electricity can we produce based on the heat sinks? Or how much car fuel can we produce based on the heat sinks? Or how much cooling can we produce based on the heat sinks? And what is the limiting volume of other types of byproducts to make full use of these heat sinks? So the heat sinks will be determining factors for the amount of energy and the quality of energy and the type of installations to be identified. Now, the third bullet of these is the one that is open for imagination and for innovative thinking. And you may well, even from the beginning, start to suggest alternate uses, but it all has to be based on a sound use of the surplus heat, and therefore you need to identify the market for heat as an energy service before we can go on into the technologies and into the supply system needed to provide this.